last speaker of this morning session, Professor Ken McLaughlin from Tulane University, New Orleans. And it will take us gently lunchtime with an introduction to Riemann-Hilbert analysis of solvent gas, just to continue in the solvent gas matter.
Speaking a slow monotone, so everyone. Thank you very much. Really delighted to be here, and I want to thank all the organizers, Magda, Vincent, Tebow, Ryan, Mark, and Kadima. Thank you very much for inviting me. When I was 12 years old, there was a kid about 4 years older than I was, and you worship the people who are a little bit older than you. And his name was Vinny, and Vinny was going to jump off the roof of the school on his mountain bike, his motocross bike. But before he did that, he went to a barber, and he just brought an album cover, and he said, "I want that," so that he would look appropriate when he jumped off the roof of the school. And it turns out that it was the police that was pointing at Sting. And I just learned this week that Sting's from this area. So what a great. Sorry? Okay. You just learned even more. So, okay, so I'll talk about, I'm going to be sampling from work with Manuela, Tamara, Bob, and Alexander. And I want to start with this movie, which is a movie about the asymptotics of a solution of the modified KdV equation. So this comes up by taking a limit of N-solitons packed on the right, together with a single faster moving soliton that's way over on the left. Okay, and the movie is a plot of the asymptotic behavior. So that means the distance between this initial point and this kind of elliptic region is the asymptotic parameter. And as the soliton moves into the region, we've computed the asymptotic behavior of the soliton, in particular, the position of the peak. And you'll see as it moves in, the peak is oscillating, and its velocity is not constant. And it was kind of one of our objectives to describe in a rigorous asymptotic way the velocity of this peak. So there you see it dancing along. Okay. Here's a plot of the velocity. So the blue curve is the actual velocity of that peak. The black curve is the kinetic theory, prediction from the kinetic theory. And just in order to connect to the conversations we've been having, in this modulated region, the local density of states is given by this formula here, and alpha is a slowly varying branch point. And if you're in this other region here, the density is sort of independent of x, and it's I guess that's the complete condensate. It's kind of a modulated condensate region. That's my understanding. Okay. So I want to be careful. I said first you take a limit in which the number of solitons packed on the right goes to infinity, and then you begin studying the asymptotic behavior of this new type of solution. And so that's described by this slide, which you can barely see. Okay, so I characterized the solution of that, the particular solution of the modified KdV equation through a Riemann-Hilbert problem, which has two features. It has a jump across a contour in the lower half plane, a jump across a contour in the upper half plane, symmetry, and then a single pole at I kappa naught and another pole at negative I kappa naught. Okay, and the Riemann-Hilbert problem. Find x. X is a 2x2 matrix. It's analytic function of the variable k in this case. Okay, and if you can find this x, then you can extract from it the solution of the PD, which is up at the top of the screen. Okay, so that's the object which we studied asymptotically when t is large, and t is large means that initial soliton has moved far enough that it's interacting with this modulating region. And actually, it's both t large and x large is the asymptotic region. Okay, so that's sort of the starting point. Is I want to sample from the work that we did to understand that picture. Okay? And of course, I want to do it for the nonlinear Schrodinger equation instead of the modified KD equation. And so just to remind us, there's the nonlinear Schrodinger equation, there's the single-soliton solution of the nonlinear Schrodinger equation. Okay. But of course, the multi-soliton solution is what I'm interested in, and so this is now before taking any limits. Okay, so I've described now a multi-soliton solution of the nonlinear Schrodinger equation. Okay, and yeah, I describe it again in terms of a Riemann-Hilbert problem. So I seek a 2x2 matrix M. It's analytic in the entire plane except at the pole locations. So there are capital N is the number of poles, a bunch of them in the upper half plane, complex projects in the lower half plane. And at each pole, M has a residue condition, which, okay, it's hard to see it from this, but what it's saying is that in the upper half plane, the first column of M has a pole. And in the lower half plane, the second column of M has a pole, and the residues in the first column in the upper half plane are related to the second column of M at those points. That's what the residue condition. It encodes in a linear system of equations, which you can use to determine the actual solution. Okay, and theta in this case is a function of z, x, and t. It's the phase function. It's written here, but the important thing to realize is that it's quadratic in z. And it's linear in x and t. Well, t times theta is linear in x. Okay, so that encodes a finite number of solitons. Okay, and what you can do if you want to is you can express the solution. It must be a rational function of z. So here it is, identity plus 1 over z minus zk times something. So those are the poles in the upper half plane, plus something which has poles in the lower half plane in the second column. And all you need to do is determine the alphas and betas. If you can find those, then the solution of your PDE is just this sum, negative 2i times the sum of the beta k star. That should say beta k star. Okay. So it's a Riemann-Hilbert problem, but you can there's many ways to represent the solution. This is one way, but of course, that there's this other way, which is just use Darboux transformations to 1 by 1 add poles to the zero background. That's another equivalent way of representing an N-soliton solution. So here's a picture of the poles in the upper half plane, the poles in the lower half plane, and the residue conditions. Okay. So what's the objective? I would like to, so you may remember in Tamara's talk this morning, she pointed out that in order to study the large N asymptotic behavior, we basically need to fix X and T in compact sense. I want to stress that and try to push as far as large in X and in T as I can and show you where the limitation occurs. Okay. To see that, you gotta watch and see how the convergence works when X and T are finite in a compact set. So for now, X and T are going to be assumed to be in a compact set. We just study the asymptotic behavior and then it goes to infinity. Okay, so the asymptotic parameter is N. N goes to infinity. The number of poles in the upper half plane, I guess there's 7 there. Now we'll go to something as large as okay, but it goes to infinity. So the only move to make is to remove all the poles at once. And so what's written up there in the white region of the screen where there's no yellowing is a definition of a new matrix A in terms of M. And so M is the thing which has poles. Okay, it's like hope, it's the thing with feathers. But that matrix sitting there after it has exactly the right residue conditions at each of the poles to remove all of the poles from M. So M times that thing, it turns out, is analytic near all those poles at once. Okay? And therefore, A is piecewise analytic. I define it in this way inside of the loop that I've drawn there, and A equals M outside of the loop. And so, so A is a piecewise analytic function, no longer has poles. A has no poles. Similarly, in the lower half plane. So now I have removed all of the poles, but of course I have introduced a jump across this contour in the upper half plane and a jump across the contour in the lower half plane. And then A is equivalently characterized by this Riemann-Hilbert problem. It's analytic in the plane. It goes to identity at infinity. And it has these jumps across those two contours. So the contours are always going to be oriented counterclockwise. All right, and the boundary values are you traverse the contour as though you're a skier, and on the skier's left is the plus side of the contour. On the skier's right is the minus side of the contour. Okay, that's convention. So now instead of having poles, I have a Riemann-Hilbert problem with a continuous, actually analytic jump across these two contours. Okay. What are we interested in? We're interested in taking these normalization constants CK as we saw this morning to be sampled R, a function R at the point ZK times some scaling so that that series is going to convert. So just to make sure I stress the similarities and differences from this morning's talk, I am not assuming randomness. I'm assuming deterministic. So I know where these ZJs are. They are not random. Okay. They're uniformly distributed between some points eta 1 and some point I eta 2 on the spike. Okay. Deterministic problem, and my Norman constants all have this feature, so there's a 1 over n in front of them. That means that if they were sort of individual single solitons, they would be shifted, in this case, probably off to the left very thin. Logarithmic amounts, log n amounts. Okay.
And it's theta 1 and 2.
The parameters, they are go back. I'm imagining that the pole closest to the real axis is sitting at I eta 1, bounded away from the real axis, and the pole at the top is sitting at I eta 2, and those are finite numbers. Okay. And so that's the setup. I'm now looking at the Riemann-Hilbert problem. And since I've chosen these normalization constants in this way, I can replace the sum by an integral. Just exactly do that. So that is this page. If you look back to the previous page, there's a discrete sum, but it's of course a Riemann sum of an integral. There it is replaced by an integral. The arrow means it's integrated where the poles work. So it's integrated on this vertical line in the middle of those contours. That problem is called, I call it Z. Okay, it was what Tamada called it the infinity problem. It's taking the limit. You have to ask, well, does it exist? So the solution, as I've described it, a solution exists. And actually, we know everything there is to know about this particular solution of the Riemann-Hilbert problem. It determines what's called a primitive potential. Psi of xt, the solution of the nonlinear Schrodinger equation, is a primitive potential in the sense that in one direction it decays to 0. And in the other direction, it asymptotes to some kind of a canonical wave. So, but brutally let n go to infinity. Okay, and the thing to ask is how well does Z approximate A? So what are Z and what are A? So is maybe like the Olympics, on the left-hand side, you've got the competitors, a finite soliton solution represented as a solution of a Riemann-Hilbert problem. The solution is called A. On the right-hand side is this limiting problem Z. Okay, and on the left you have a finite n soliton, a finite number of solitons. On the right-hand side, you've got some kind of elliptic wave, like some kind of primitive potential. Okay. How do you compare them? Well, you form this ratio. E is the error between them. It's A times the inverse of Z. Right? And E solves a Riemann-Hilbert problem, which has these jumps. So across the contour in the upper half plane, E plus equals E minus times the jump matrix identity. Plus, and this is the nice part, it's Z minus and Z minus inverse, conjugating something which is clearly small, right? It's the difference between the integral and the Riemann sum. Okay. In the lower half plane, it's the same thing, but it's the triangularity is reversed. Good. So this is small. In fact, okay, depending on what kind of assumption you make on R, you can probably make this order 1 over n squared. or maybe even better, it's up to us how we choose the function, okay? So if x and t are bounded, then I know that the z is bounded, and also z inverse is bounded. And this difference between the Riemann sum and the integral is order of 1 over n to some power. So I can rewrite this Riemann-Hilbert problem in this form. So if you stare at the top and stare at this, you should see, okay, it makes sense, right? E plus minus E minus, that means I've moved the identity term over the other side. E plus minus E minus equals E minus times something which has got order n to the negative capitals, or some capital. 1, maybe it's 2, depends on how lucky we are with our discretizations. Okay. Okay, so I'll rewrite this formula on the next screen. Okay. And well, you can't really, okay, it's up there at the top, almost hidden by the green and blue of the soup, but you can still see it. So now I maybe that I'm the only one that wants to do this, but I want to explain small norm theory. And so here's the one fact about Riemann-Hilbert problems, which is probably hopefully everybody will enjoy either relearning or seeing for the first time. So up there is something I call E tilde of z. It's just the Cauchy integral of a function f divided by s minus z, and I'm integrating that on both contours. Okay, both loops. Gamma represents both contours. That integral satisfies this jump relationship. The plus boundary value at a point zeta on the contour minus the minus boundary value at the point zeta equals the integral, equals that, the numerator. Okay. So that's called the Cauchy-Flamel-Stokhatsky formula, but in any case, that's the very useful fact that connects this Riemann-Hilbert problem to, okay, complex variables. So what you do is you just rewrite that boundary, E plus minus E minus equals the right-hand side, and you jam the right-hand side and replace it by F. So that's what's written here. Instead of writing down a Riemann-Hilbert jump relation, you write this down. E equals, okay, some constant matrix identity plus exactly the thing that has the right jump. Okay, so I've just re-expressed that jump relationship using the Cauchy integral formula. Is cool? Okay, so it's implicit, right? It's implicit. But now I can take boundary values in which I let, in this equation here, I let z approach a point zeta on the boundary. So this should be, yeah. So this is E minus of zeta, so I'm letting z approach zeta from the minus side, equals identity plus the limit as z approaches zeta from the minus side of this integral. Okay. I rewrote it down here. E minus equals identity plus. Okay, this notation is an operator which represents this limit. It's called the Cauchy boundary value C minus. C minus of this density E minus times Wn. Okay. And E minus times Wn, the Wn is the thing which is order n to the negative kappa. That thing is small. E minus is unknown. But if you stare at this bottom line of the screen, you say, okay, that is an integral equation. Right, for E minus. Okay, so next slide is going to repeat that integral equation. There it is. An integral equation for E minus. Okay, and Wn is somehow small. Order n to the negative kappa. So here's the only well, I guess I should rewrite it one more time. So instead of calling it C minus of E minus times W, I introduce a new operator called J. J is just that operator. Okay, so J of something is take the thing, multiply by Wn, and then do a Cauchy projection. Cool. All right, so here's what you know. The Cauchy projection operator is bounded in L2 of a contour. That's the only harmonic analysis that I need for this presentation. And okay, it means we have to imagine understanding what is L2 of a contour, which is a little bit annoying. But But if you accept that for a second, the L2 norm of J as an operator is equal to the L2 norm of C minus of A times W, and C minus is bounded, so I extract a constant K times the L2 norm of some unknown H times Wn, but Wn is bounded in L infinity, bounded by 1 over N to the power kappa. So I have that the operator norm of J is bounded by a constant times N to the negative kappa times the L2 norm of H, which means it's a small norm operator. Okay. The integral operator has small norm. And that means that this equation sort of E minus J of E minus equal to negative, that can be solved by Neumann series. And I'm skipping the details, but what you learn is that the E itself, the solution is identity plus something uniformly 1 over N to the kappa plus, 1 plus mod Z. Happens to go to 0 as E goes to infinity. So that's small norm theory. Why? So E exists and E has a Neumann series and E has an expansion like this. Okay. So remember that E was the ratio of A times Z inverse. I now know completely separately that E exists and has an expansion of this form, identity plus error terms. You just jam that in and you learn this. A, which is the object which characterizes the N-soliton solution, is equal to E times Z, where E has got this expansion. Eventually that shows you that psi n, the N-soliton solution, is equal to the primitive potential object plus an error term equals 0. Okay. Cool. It's kappa was the error rate, right? So I have this. Sorry for this. It's the Riemann sum minus the integral goes to 0 like some power of n. That's what it is.
It's given.
It's given. Yeah. You know what that is. Yeah, that's right. Okay. So I flashed this up here. This was the original Riemann-Hilbert problem, and this kappa came from the difference between the Riemann sum and the integral. And what I have used is that for x and t bounded, the solution to that Riemann-Hilbert problem is known to be bounded. That's all that you need. And the conclusion is that, the N-soliton solution converges to this primitive potential when n goes to infinity, as long as x and t are bounded. You could add an extra pole. The extra pole at the top and bottom, that doesn't affect this. That's fair. But what goes wrong? You may remember in this movie that I said that was asymptotics in x and t. So when x and t are growing, I'm skipping all of the details of how you compute the asymptotics of z when x and t grows. But I'll tell you the punchline from that is that z itself has exponential growth in x and t. Okay. So does the e to the theta, e to the 2it theta, that also has exponential growth in x and t, but it's not worse than exponential. Bounded by e to a constant times either x or t, depending on which is the big parameter. Okay. So it's bounded exponentially by x and x and t.
Real? I mean, exponential real expansion?
This c is a complex factor variable. It's on that function. But it's
Bound x and t
with some constant that depends upon c.
which will compare.
Yeah. Yeah. Why? In any case, the worst case is some maximum. There's some maximum, like either some constant times x bounds the growth of c. Okay. Cool. Yeah, okay. So now there's a competition. Okay, the competition is how does the exponential growth here versus the decay in 1 over n here, how do those play off? And so once you see, you think, oh, well, probably there's some slow growth rate where I can still manage to get an error that goes to 0. Okay, and so this is just to remind you, the picture that we're talking about is an asymptotic result for this primitive potential after having taken the limit as n goes to infinity. Right, so remember solitons already went to infinity, and then we did asymptotic. So instead, I don't even want to show you the movie. instead, here's the configuration. Okay, so I have now N-solitons. Their locations are written up there explicitly, and my normalization constant is some. Okay, I is just imaginary. Negative I over N times R of Zj, and that's the kind of smaller pole that you see there. Okay? And then there's a tracer soliton, which has got a pole location at Z0 and Z0 bar, and there's normalization constant which is written up there. If you look at that normalization constant, you see a log N. That means I push that soliton off to one side. I forget which side. Off to one side far enough that you have to wait log N time before it begins interacting. And there's a delta in front of it. So delta is a small positive constant. Okay, so that's the setup. This is now a finite soliton problem. Probably can be evaluated numerically. The number of solitons might be 200, and the time scales in which we need to evaluate things is logarithm. Logarithm 200. So now I want to evaluate this at time. Little t is time, capital T times log N, where capital T is in some small window, delta naught to delta 1. Those are two small numbers. Fixed positive, but small numbers. And then evaluate x at a constant times log N, where x over t happens to be in this window. Okay, so 4 eta 1 squared is sort of the characteristic speed at which the elliptic wave starts. And V2 is the characteristic speed at which the elliptic wave stops being modulated. Okay. What I know in this region is that the N-soliton is still well approximated by the kind of primitive potential, plus an error term that's now for some kappa positive lost some rate because I've evaluated some logarithmic distance in x and in t. But I choose the delta small enough so I still have 1 over n to a probably smaller power kappa. Okay. Now, that's just comparing the finite n solution to the primitive potential. The asymptotic, the primitive potential, and there's another error, but is of the same size. So instead of being in the negative kappa, it's in the negative kappa hat for some slightly smaller kappa. Okay, so that's sort of the best that we can do using the existing analysis is you can get logarithmic distance in x and in t, but it's a small constant times logarithmic distance. And you may remember what Tamara says, we need to get log n distance in. That means not a small constant times log n, but the actual full order 1 times log n amount inside. And that's really where the analysis breaks down. So on the other hand, you do know that the N-soliton solution is going to be exponentially decaying eventually. And how large does x have to be for you to get past all of the solitons? Well, probably n log n. Just if you're that far away, then you're past all the solitons and the solutions again decaying. So that poses an interesting question. Determine the uniform behavior of this N-soliton solution over varying time and spatial scales that range between like small constant times log n and n log n. That whole region is a region in which the analysis that we've done just doesn't apply. It all flies off to infinity to let n go to infinity first, but it's a region where there's significant changes from the elliptic wave. That's
Questions?
I guess you could also just not take the seats, right? Not divide by n. You can't get it into, but that's what you want to do.
So that's a different problem that
You don't, what I'm saying is that in that intermediate region, solid, yeah, you don't expect it to look like.
Yeah, I agree. Yeah. In that, so what I think happens in that region is, we put a 1 over n in, but now that is sort of completely eradicated by the exponential growth of z and even t beta. It turns out that sum is now order n times something right there. And so you have to sort of grapple with an n which sits in both off diagonal and ordering problem, and there's some other sort of d function you see there.
Can you control the distance between the poles?
Oh, yeah. They're, what I said in here was like, where did it go? I said
Right
something.
there. Oh, no.
I passed.
Right there.
What about that? Yeah. But here they're 1 over n. Right?
Okay, so.
Pretty sure if I like this.
Yeah. This is very specialized, they're uniform in space, but that doesn't have to be, so it's, but certainly what constant over n probably accept at top of it.
There are no questions, let's then. Can we get